All right, this should be recording. Good evening, everyone. This is supposed to be another supplementary video that should help you guys consolidate the stuff that you learned already. So we just finished some resonance, and we also finished thermodynamic and kinetic product. And he kind of threw a lot at you, and we're already moving on to substitution elimination reactions. And that's just a lot of stuff you have to deal with for test 3, which is already next Friday. So let's go ahead and just jump into it. Also, I bit my tongue earlier, so there might be a little bit of a lisp. Yeah, let me go ahead and share my screen. There we go. All right, you guys should see my screen right here. So what I have right here, they're just some practice problems I pulled from 2021. You won't see this in your test 3 material. This is just supposed to be like video exclusive. It's just some new material that should give us some practice and just be our template on how we approach all the other things. So really quick, let's just go ahead and review our resonance structures. So ideally, you're kind of getting a grasp on how resonance structures work, the approaches on just how to draw valid resonance structures, and then how to decide the most stable one. That's essentially all we're trying to do, at least for this test. And I have a video entirely dedicated to that. Okay. So using the information from that previous video, all right, we have our resonance structures. And looking at this, we need 2 other valid resonance structures. So the first thing I usually do, identify that net formal charge. So net formal charge is +1. There's only one positive formal charge, all right? And that should set the rule for all the other ones. The net formal charge for all other resonance structures should be +1, okay? Now, let's go ahead and build our structure. So looking at this right here, I'm just going to go ahead and draw my sp or label my sp2 carbons. sp2, 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 and sp2. Okay. I'm going to draw X's over my sp3s so that I know, all right, well, these are sp3 carbons. They have 3 hydrogens, or just basically 4 domains, 4 sigma bonds. They do not play any kind of role in resonance structures. Okay. Because they don't have any lone pairs. They can't donate or accept pi electrons. And by pi electrons, I mean a lone pair or a pi bond, because that's kind of what we move around. We move around a pi bond, lone pairs in the form of a negative formal charge, or the lack of a lone pair, which is that positive charge that we're seeing right here. So we identify our boundaries. I'm just going to redraw my carbon skeleton. Okay. So redrawing my carbon skeleton, well, one of the moves that I can do, if you already memorized them, which you kind of need to do, door hinge. All right, I have a positive charge right here. I can just conjugate my alkene over and door hinge that positive charge over there and just trade places with it. All right, and let's look at that. The net charge is +1. All right, let's look at it again. Let's redraw it. Okay, well, for this alkene, if we move that one back, we would be back to where we were. So it wouldn't really be a new resonance structure. For this alkene, if we door hinge that over there, well, positive charge would be here. Now our alkenes are right here. Look at that. The net formal charge is +1. These are valid resonance structures. Now, looking at them, which one contributes most to the hybrid? Which one's the most stable? Well, looking at over here, we got secondary carbocation, tertiary carbocation. Okay. Additionally, the thing that I probably should have identified first, let's look at the number of bonds. All 3 have the same amount of pi bonds. So we can't really use that as a determinant, because remember, for all of your resonance structures, whichever one has the most amount of pi bonds is automatically the most stable. Okay. Same thing with the least amount of formal charges. On top of the most amount of bonds, we also want minimal amounts of formal charges, because it's not very kosher. It's not what atoms really want. But for this situation, they all have +1 formal charges. All right, so they all have 2 pi bonds, 1 plus formal charge. So now let's just look at the stability. Tertiary is the most stable, so it's going to be this one. Now let's look at this structure. Let's look at that positive. The net formal charge is +1. +1. Okay. So then all the other structures should be +1. +1. Okay. Now looking over here, we need to do again, the moves we memorized. Now, let's identify. We have an sp2, 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 sp3 carbon, sp3 carbon. Look at that oxygen. That's sp3. However, it has lone pairs. So it can hypothetically donate those electrons, or except depending on the situation. But for this one, it can only donate. Okay. Now, this one, though it can only donate, it can't really donate anything right now, because if those lone pairs go here or here right off the bat, well, can't really do that because let's look at it. If the double bond was formed right there, you can't do that because this carbon already has that one hydrogen. Adding another pair of electrons or pi electrons would exceed the octet rule, which is not what we want. Nor can we move it over here and do the same for that carbon for the same reasoning. That carbon already has two hydrogens. We cannot add those pi electrons there. All right, do not do that. So what do? Well, if we can't start from down there, let's look if there's anywhere else we can start, which we can. We got a pi bond right here, and we have a carbocation. Hypothetically, you could just break the pi bond and put the lone pair on one carbon and then leave a positive charge somewhere else. But that's not a very good resonance structure. That's three formal charges. Not what we want. But like what we did before, we can just door hinge it over. So let's redraw our carbon skeleton. All right, if we door hinge that lone or that pi bond over there, the carbocation would be over here. All right, let's look at net formal charge, +1. Can we go further? Yes. Now that there is a net formal charge, or now that there's a formal charge of +1 there, that hydrogen, this carbon, it's still sp2, but now it just has an empty p orbital where we can drain those electrons. So let's draw it out. One pair right there. Because those two electrons became that double bond. All right. Those lone pairs, I'm just going to redraw it. That was right there. And if you look at the formal charges, well, the formal charge has to go somewhere because the net formal charge has to be 1. And if you look at it, it's going to be oxygen. Oxygen has 3 sigma bonds. It normally wants 2 sigma bonds. So as an extra one, it's a positive charge. Okay. Now, looking at this straight up, all of them have the same formal charges. So they're all valid resonance structures. Now, which one is the most stable? Remember, for our rules, the most amount of pi bonds is automatically the most stable. Looking at the first one, there's only 1 pi bond, second one, 1 pi bond. However, if you look at this third one, you got 2. It's automatically the most stable. It's going to be that one. Now let's look at the meat of the content that I kind of want to get to. We're looking at 4 different products. This is going to be a page on your test. This is what the mechanism page will look like. It's going to be worth a good amount of points. Okay. Now, notice here, we have our diene, a conjugated diene complex, diene X, and we're reacting with HBr. It could be HI, HCl, same kind of deal. It's our normal reaction. The less E, more nu. Our hydrogen, our electrophile goes to less substituted carbon on that whatever alkene it is. And then the carbocation forms wherever the less substituted that hydrogen is not, which is where the nucleophile will add. All right. Well, if you look over here, we have 2 alkenes and we have 4 products. And if you look right here, bromines on this one, bromines on that one, bromines on this one, and bromines on that one. There's 4 different spots bromine added to. Well, if you look over here, bridgehead carbons on that alkene, more bridgehead carbons. Well, look at the pattern. We added bromine to every single position that those diene carbon heads are. You might be thinking, how is that possible? Because if we add our HBr normally, shouldn't the H always go in the less substituted? For example, if we were to add on HBr to this one, right? There's absolutely no way BR can go there because that's where the H would go. Yet product 2 does exactly that. However, gotta watch yourself. No, it doesn't. Look at where this alkene is. It conjugated over. And you'll see how we kind of got those later on. But I just want you to keep in mind that, I don't know what I'm trying to say. Just keep an open mind. I'll show you how all of these products turned out. Okay. So show the stepwise mechanism for the formation of product two. Show all intermediates, formal charges, and resonance structures. All right. Keeping that in mind. All right. So product two. All right. That's the one we're trying to make. So for our initial alkene, something like this here. Let me redraw it. There. Okay. Now A or B? Well, let's say we were to react with A. All right, hypothetically, just react with A. All right, alkene breaks. Let me use red. I like red. All right, the H would go here, so less substituted, and that carbocation would form there. All right, that's what we know. All right, now let's draw a resonance structure. Remember, you got to do the double-sided arrow. All right, that's an entire point on the test. On the answer key, literally, there's 1 point worth for that double-sided arrow. If it's not double-sided and you don't show that as a resonance structure, it's incorrect. And if we look over here, or what I'm about to do, so I'm about to door hinge this over here because an sp2, 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 and a allylic carbocation. All right, try to redraw it. H, carbocation right here. These are resonance structures. They all have the same net formal charge. And now we have, remember, our floating Br ion, our nucleophile. All right. Now, let's say this Br were to do a nucleophilic attack on that carbon. Okay. If it were, you would get product number two. Look at that. Now, here's the kicker. What if we added Br over here? I'm going to do a dotted line just to show a hypothetical. Okay. If we had done that, we got our H, I got our Br, this product number two. Well, if we didn't conjugate over, that's our product one. This is our 1,2 addition. This is going to be our 1,4 addition. And you might be thinking, well, Patrick, how on earth did you get that? Well, let me show you. So if the 1,2 and 1,4 addition labeling, it's relative. It's relative. So if we were trying to react with alkene A, for example, all right, 1, 2, 3, 4. Again, relative. We're not trying to name it. 1, 2, 3, 4. Well, if we added to our 1 and 2 position, that's our product one. 1 and 2. Okay. Conversely, if we added, let's say 1 and 4, that's our product two, where we conjugate over. So our 1,4 addition is always when we add to an alkene, but that conjugated diene, the alkene conjugates over and forms a resonance structure, so it extends it. Because remember, resonance is basically delocalization of electrons and the delocalization of charges. Okay, so if the 1,2 addition is really close, there's no resonance. Well, resonance, if you're delocalizing that charge, 1,4 addition, you're adding it to two separate places. Well, in both situations, but you're adding them farther. Okay, and I'll show you another example later on down here, but we already have product one, product two. Well, how do we get product three and product four? Well, I'm about to show you, but let's react it with alkene B. Okay, well, alkene B, let's go and let's just do it. So for alkene B, we got our HBr, and this one's asking us to make product number three. Okay, well, if we look over here, product 1 and 2, there's absolutely no way we can make product number 3 because we can't. Because in order to make product number 2, we had to break the A alkene, and product 3 cannot be formed from that A alkene. Let's just go ahead and break it. Let me stop babbling on. I forgot my lone pairs. Okay. H, positive charge. All right, that's our first resonance structure. That's our intermediate. And our intermediate is carbocation, because remember, carbocation intermediates for HBr. That's one of the 3 reactions you have to know. There's carbocation. There is resonance. So if I were to hypothetically conjugate or door hinge that double bond, or that pi bond over and trade places, that positive charge would now be here. And H is still there. There we go. Okay. The net charge is still positive 1. Now we have our free-floating nucleophile, Br bromide. Let's say it were to add over here. Okay, if we're to add to that carbocation, you would get something like this. BRH. Whoops. And for the other side, add here, you would get BR over here, then H. All right, well, let's look at that. Product number 3 is product number 3. It's product number 4. Look at that. Product number 3 has a bromine right here. That's exactly what we did with that alkene. A is still there. All right. Now let's go ahead and try labeling this 1, 2, and 1, 4 addition. Okay. So if we're looking at alkene B, remember, let's keep it relative. If we had the normal 1, 2 addition, 1, 2, 3, 4. Again, remember, it's relative. Relative 1, 2 addition. Well, if we just added across the 1 and the 2, well, that's product number 3 right here. We added to the 1 and to the 2. Right? 1, 2, 3, 4. So our product 3s are 1, 2 addition. And this is obviously our 1, 4 addition because it's not the 1, 2, but let's go ahead and just prove it. All right. We're looking at alkene B, which is what we reacted with, 1 and 4 addition. That would give us product number 4. Our hydrogen went to that first carbon. Bromine, or our nucleophile, went to that 4th carbon, right over here. Now let's go ahead and start analyzing what just happened. Okay, so what just happened is we identified how this conjugated diene, the diene X, is able to form 4 different products. All right, each alkene can form 2 products. So alkene A forms 2 products, its own 1, 2 addition, and its 1, 4 addition is when that other alkene conjugates over and delocalizes and sends that positive charge over there, and vice versa. Product 3 and 4 arises when we react alkene B. Alkene B has its own 1, 2 addition and its own 1, 4 addition when we conjugate or door hinge that other alkene over. Remember, they have to be conjugated, all right? If they're not conjugated, if they're isolated, they're far away from each other, they can't door hinge over, and you won't really have this cool system, all right? So hopefully that made a little bit of sense. You're welcome to rewatch it, but I'm just going to go ahead and move on with the analysis. So when you're dealing with thermodynamic and kinetic product, that's the little itty bitty part it's not really itty bitty, but it's going to be confusing. Okay. The great thing about 1, 2 addition, no matter what, your 1, 2 addition is always your kinetic product. No matter what, your 1, 2 addition is always your kinetic product. I'm going to repeat myself. Your 1, 2 addition is always your kinetic product. All right. It likes cold temperatures. It has a low activation energy, but also is not as exothermic. There you go. Not as exothermic. All right. Your thermodynamic product is a higher activation energy, but also more exothermic. Now, if your 1, 2 addition is your kinetic product, we technically do have 2 kinetic products. So this is a kinetic product. This is another kinetic product. All right, now let's look at product 2 and 4. 1,4 addition, most of the time, your 1,4 addition is your thermodynamic product, most of the time. There are exceptions. Sometimes your thermodynamic product is the same as your 1,2 addition. And the way you decide that is looking at the substitution pattern. If you remember from test 2, you would be asked, all right, look at this alkene and identify its substitution pattern. Is it mono, di, tri, or tetra? All right. And the way you deal with that is you look at how many carbons those alkene bridgeheads are connected to. So what I mean by that is if your alkenes are right here, those are your sp2 alkene carbons. Look at how many carbons connect to. 1, 2, and those are hydrogens. Those aren't carbons. So if it's connected to 2 carbons, this is di. To give you another example, what if you had, all right, something like this. Okay, again, your bridgehead, your alkene head carbons. How many? It's connected to 1, 2, 3. You don't count those bridgehead carbons, but how many carbons is connected to outside of that alkene? And that's 3. That's going to be tri. So using that same logic, your thermodynamic product is the one with the most substituted pattern. So like mono, di, and tri. I'm going to use a different color for this one. Let's use lavender. Okay, so let's look at product 1. If our alkene for product 1 is this, okay, let's look at our bridgehead carbons. I'm going to use that blue again. We got 1 carbon, 2 carbon, that's di. Okay, so look over here, bridgehead carbons. Let's look at our carbons. 1, 2, 3, 4. That's tetra. If we're looking at di versus tetra, which one's our thermodynamic product? It's going to be the most substituted. It's going to be tetra. So in this case, our thermodynamic product is the 1,4 addition. So product 2 is a thermodynamic product. Now, looking over here, let's do the same deal. All right, let's look at product 4. Bridgehead carbons, 1, 2, 3, 4 carbons. It's going to be tetra substituted. Let's look over here. 1, 2, or that's not 1, 2, but those are bridgehead carbons. It's going to 1, 2, 3. That's tri. All right. Tetra and tri, which one is the most substituted? It's tetra. So our thermodynamic product is here. So product 4 is another one of our thermodynamic products. Now, let's get to this bottom part. Which double bond, A or B, is the most reactive? Well, let's take a look at the substitution pattern. Well, for this one, our carbocations, I use carbocations, tertiary and secondary. Okay. Up here, we have tertiary and primary. All right. Which one's more reactive? Tertiary, primary, tertiary, and secondary. It's going to be B. It's tertiary and secondary. You can also look at the substitution pattern. All right. Now, which product 1, 2, 3, 4 is a kinetic product? Note, there's only one, and they're right. Well, obviously, Dr. Berg, he made the test. There's only one. And you know, from the analysis we did, it's either 1 or 3 because 2 and 4 are thermodynamic products. So it's 1 or 3. Which one is it going to be? Well, I'll give you a hint. Look at that. 3. Because product 3 is derived from the most reactive alkene, B. All right. Now, which one's the thermodynamic product? Let's do the opposite of what we did. 1 and 3 this time are excluded because those are kinetic products. 2 or 4, which one is the most, or which one is the thermodynamic product? And you might be thinking, well, shoot, we got tetra and we got tetra. Well, look at the most reactive alkenes, B. This one's secondary. This one's primary. B's our most reactive alkene. All the signs point to here. It's going to be a product 4. That's essentially how you do thermodynamic and kinetic product. So just to reiterate, just a quick little summary. All right. So we have a conjugated diene. Conjugated means you have the sp2 carbons 4 in a row like this, so that if you were to add an HBr or just have a carbocation intermediate, it could be delocalized and door hinged over. So that's the point of the diene. Okay. Now you have 4 products because you have a diene, and there's different places where you can add. Each alkene can react with the HBr, and it can be delocalized or just normal 1,2 addition for each alkene. So a total of 4 products. Additionally, each alkene has its own kinetic product and its own thermodynamic product. The kinetic product is always going to be the 1,2 addition. And the thermodynamic product is always going to be the most substituted alkene, no matter what. And the thermodynamic product, it could be the kinetic product. Your kinetic product, your 1,2 addition, could be the more substituted one. And if it is, it's the thermodynamic product. All right. And if you're looking at the most reactive one, it's whichever one is the most stable. All right. So you're looking at carbocation, substitution pattern, and then the alkene substitution pattern. They'll align. So don't worry about picking which one, they'll align. Then which product, 1, 2, 3, or 4? Well, you just use, this is what I did. Essentially, you just use the alkene you use, and the products that alkene forms, those are going to be your kinetic thermodynamic products because it's the most reactive alkene. All right. So hopefully this helps wrap your head around this concept, and you should be able to do this on the test. I have a video on SN1, SN2, E1, E2 coming out. Actually, it's not coming out. It's already recorded. It might be in the same announcement as this one, but it should help you with the problem set. All right. So I'm going to stop my share. Feel free to email your TAs if you have any questions. All right.